It's our pleasure today to have Ian and Charlesworth from Cardiff University. Ian is going to talk about graph products and the strong one founded. So, Ian, please take the floor.
Yes, great. Thank you. Thanks for the invitation to speak at the seminar. It's fun to come and have a chance to talk about the sort of stuff I'm doing. So this whole thing is a joint project with Rolando, Ben, David, Shri, and Brent, which we started working at an AIM workshop down in San Jose. It's quite nice. So thanks to AIM for the American Institute of Mathematics for funding us. So I want to tell you a little bit about graph products, which are these things we've been studying, and these have come up with many different names and many different settings, but they're the same sort of idea, which is we want to have some kind of mixture of free independence and classical independence, or some mixture between free products of groups and direct products of groups, or something like this in the von Neumann algebra setting. So before I get too deep into it, as far as I'm aware, the first sort of introduction of this kind of mixture of free and direct product was in the setting of groups due to Green, in her very common last name, introduced graph products for groups. No, not Phil Green. Introduced graph products for groups in, I think it was the 1990s, although I could be wrong on that. I'm not very good at remembering dates for groups. And then as far as I know, the first introduction in the operator algebra setting was due to Mwatkowski in the mid first decades of the 2000s, and he referred to them as lambda free. He referred to the concept as lambda free independence. It was then 10 years later introduced again by Speicher and Wysochansky. And they referred to the thing as epsilon independence. Everyone has a different name, and then independence. Finally, it was reintroduced again by Moram. Wait, no, got to check the spelling. Sorry, it's important due to Morampudi and Laumann, but I don't know how to spell, and I've also lost the spot in my notes where it says this, and that's embarrassing. Okay, well, I'll make a best guess, and my apologies for the misspelling. Morampudi and Laumann. And they refer to it, they're physicists, which is why it's in ML order, not LM order, as heap-free independence. Pardon me? Only, well, they're theoretical physicists. Independence. Okay, and so I'll tell you a little bit about what this concept actually is, and let me just say, I was talking about interpolation between free and classical independence, and this really was Mwatkowski's motivation. Back in the early 2000s, people were very interested in studying these Q-deformed Gaussian distributions, and the question was whether you could find a setting where the Q-deformed Gaussians were the central limit objects in some sort of Q-deformed central limit theorem. And we know now, due to work of Speicher and Meraki, Speicher and later built on it by Meraki, that there are only 5 independences. And so you can't have Q-deformed Gaussians arising sort of naturally as one central limit thing in one cohesive probability theory. But if you allow this sort of mixture and a more delicate theory, then you can have them showing up. Okay, so what is the input data and what is the independence relation? So graph independence, or lambda, this concept, independence, dependence. Okay, so it is built out of a graph or a relation, symmetric relation on a finite set, if you like, which will be G. So G is going to be a vertex set and an edge set, and this is a simple undirected graph. So no self loops, 1 or 0 edges between any pair of vertices, and if there's an edge in one direction, there's an edge in the other direction. Or there's one edge and it's bidirectional, if you like. And we also get for each vertex in the graph a tracial von Neumann algebra MV together with tau V. And then we want to build, we're going to build a larger von Neumann algebra, which is generated by all of these individually so that they have some kind of mixture of free and classical independence going on. So MG is generated by copies of MV by all MV, and it's built in such a way, and I'll tell you the precise way in a second, so that if I look at MI and MJ, or MVI and MV and MW, let's say, these are tensor independent if there's an edge from V to W. And freely independent if there is no edge. Okay, and so when Matkowski was trying to build these settings for Q-deformed Gaussians as central limit sums, what he realized is that if you take a countable family of von Neumann algebras and you say index by the natural numbers, and then you put a random graph structure on them in such a way that like it doesn't have too much structure to it, and he makes that precise, but I'm not going to bother. Then in the limit, you get a Q Gaussian arising from a central limit sum of variables coming from the individual algebras, where Q is determined by the density of edges, or the limiting density of edges, as you take larger and larger subsets of n. And so that's how this is coming up. And the point is that like if you want the zero deformed Gaussians, which are the semicirculars, then you should take every single pair of algebras to be free, and you should have no edges in your graph. And if you want the normal Gaussians, then you should take everything to be classically independent. These are the one deformed Gaussians, and you have density 1 for edges in your graph. Okay. I'm not certain. I thought they had, didn't they have cross products showing up in that? No, was it? Okay. Yeah, it certainly could be. I'm not deeply familiar with that work, so it would be worth looking at later for sure. Okay. So let me tell you formally how this is actually defined on the entire algebra. And as well, this sort of will hint at how to show how to define, well, yeah. I am a free probabilist, so I'm going to tell you how to define this thing by telling you what the state should be on the algebraic free product of all the algebras. And then that should also hint at how you actually construct one of these by taking some kind of pointed Hilbert space product and taking an appropriate product on an appropriate inner product on a tensor product of pointed Hilbert spaces. And there's a way down there, but okay. So how do we define? How do we define it? Okay, so first of all, it's going to be, let's say, I'll start with a definition that leaves one sub-definition to be given, and that's suppose that I am in this setup. So I have a bunch of tracial von Neumann algebras indexed by some vertex set, and let's suppose. Well, yes, yeah, simple graph. It's whenever I talk about combinatorial objects, I always assume they're finite. I had a friend in graduate school who made the joke that the first fundamental theorem of combinatorics is that all sets are finite. So, we're adopting that when we define graph. Okay, sorry. These are, in fact, rather these are sub-VNAs of one large tracial VNA. M tau. then they are graph independent with respect to a fixed graph G. If we have the following. First of all, that they commute whenever there's an edge between them. Whenever VW is an edge. And second of all, and here's, yes, it was in my head, but didn't make it onto the board. No, not yet. It's like this awkward height where this is a little bit too low, but I can't put it up in. Yeah, but then you can't see. All right. So this is the bit where I'm going to shuffle off one definition to give you in a second, which is to say that if I have Vn is, so this is a finite sequence of vertices, and I want it to be G reduced. And I take xi in the corresponding von Neumann algebra, von Neumann subalgebra, with trace 0, xi equals 0, then the entire product as trace 0. Okay. And so this should remind you a lot about the definition of free independence, right? If instead of G reduced, I just said alternating, then I would have defined free independence for you. And if instead of G reduced, I wrote in all the letters are unique, then I would have defined classical independence for you. Not in the usual way, but something equivalent to it. And so the point is that by putting in the right structure of G reduced here, then I get this notion that is an interpolation. And what's the intuition? Well, in both free and classical independence, the thing that stands in for G reducedness is supposed to say that each word has one sort of base representation, but you're not over defining or over constraining things, right? So in a free product, the reason we rule out adjacent letters coming from the same algebra is because I could just do the multiplication in that algebra and get a simpler word. And in classical independence, the reason I rule out ever picking the same algebra more than once is because I can just commute them to put those two together and do the multiplication in the algebra and get a simpler word. So the point is, this notion of G reduced is exactly supposed to be correspond to those products of variables that I can't simplify by knowing the structure on the individual subalgebras. That's exactly what it's trying to capture. And so how do we write something down to capture that? So the definition is that a word v1 through vn in the vertex set is G reduced if whenever I have I less than j with v, where I've picked the same letter twice at two different indices, there is some k in between them, so that vi vk is not an edge, so that the algebra corresponding to the kth vertex does not commute with the algebra corresponding to these two vertices, or to the algebra corresponding to the vertex with these two labels. And so again, the point is, if there were no such k in between two of these things, then they would commute with everything in between, and I could move them together and reduce the length of my word. So these are sort of the minimal things. And that's enough to sort of run the whole free probability style arguments and show that this recursively defines this is a condition that tells you how to compute the trace of any arbitrary product by reducing it into some complicated polynomials and traces of things coming from only one of the algebras.
Same with say there's a k such that k comma bj as well.
Yes, because vi equals bj.
Oh, vi equals bj.
Yes, and the edge set is symmetric. Yeah, we don't have directed. Was there another question? No.
We'll pose the same question.
Yes, which is why I was ready for it.
I mean, whatever you need to just going to be not. People don't care, but I mean, if anybody ever cares, I guess it should be okay.
Yeah, I mean, I suspect it will probably work. Yeah. There might be something to check on the, like in the Hilbert space construction, maybe you need to be a little bit careful about the things you're modding out by, but yeah, I agree. I think it should be okay. It's certainly not the case that we're interested in. And the first fundamental theorem of combinatorics applies.
These things that Schleifer and River was used to create few Gaussian central limits, those are infinite.
Matkowski. Well, so he had a limit of finite ones. Like he never took I mean, anytime you take a product, you only have finitely many terms. Yeah. But yeah, I suppose he took an increasing family of finite subgraphs of an infinite graph. Yeah. Okay. Good. So this is the kind of thing we want to study. And we're particularly, oh yeah, right. Let me give you a couple examples to keep in mind. And so the simplest ones are, well, like I was saying earlier, if you replace the statement of G reduced here with just saying no two adjacent letters are the same, you'd have a definition of free independence. And that corresponds to a notion of G reduced just saying that there's a different K in there. And so if you think about it for a little bit, it's not so hard to see that that just means that your graph was the empty graph, or the graph on n vertices with no edges. So if G is equal to V empty set, then G independence is just free independence. For a family of this many things. And on the other hand, if you had a complete graph, if you had a clique, if you had V and well, V squared minus the diagonal.
You want to say that it's a complete graph?
Yeah, if G is a complete graph, I'll just write Kn. That's an easier way. Then G independence is just tensor independence. Independence. Right, and again, that comes down to just this condition here is saying that, well, everything commutes with everything, so you're never allowed to pick the same vertex twice and be G reduced. So you just have tensor independence in this case. And then there are some graphs you can sort of play a little game and use combinatorial structure to reduce it to simpler graphs, right? So if I have, for example, well, if I have a graph, well, let's just take the box. If I have the box with 4 vertices, then I can recognize this as being, I can rewrite this as 2 disconnected vertices and 2 disconnected vertices, where every vertex on this side is connected to every vertex on this side. It's a complete bipartite graph, which means that what I really have is the the tensor product of these 2 families. So this corresponds to, if I label my vertices 1, 2, 3, 4, the free product of M1 with M3 tensor the free product of M2 with M4. And for nice enough graphs, you can find a decomposition like this and you can break them down into simpler things, but it's pretty easy to come up with examples of graphs that can't be reduced in this method. Right? In fact, if you just take like the path of length 3, then these tools don't tell you exactly what it is. Although I suppose there it's still not the worst. That's a manageable one. But you can start drawing more complicated graphs that don't decompose into nice pieces pretty easily. Okay. So the kinds of questions we want to ask are, if you have one of these graph product von Neumann algebras, what kind of von Neumann algebraic properties get preserved? What can we say about its structure? What can we say about how it behaves? And you know, a few results from history. For example, Casper's showed that graph products preserve R omega embeddability. Embeddability. 2Ds. I'm not sure how to spell embeddability. 2Ds, I think. 2D. Yeah, there we go.
But there's a discussion whether it's an A or an I coming after the two Ds.
Is there a discussion?
Well, it depends on the dictionary.
Uh-huh.
Anyway, I'll accept that.
I'll put an O there just to be contrarian. So now I'm certain that I'm wrong.
That reminds me of your writing so instead of such. I mean, which is an adverb can't modify a noun or a complement.
Yeah, I'm very radical with my approach to language.
Well, it's if I were a little more brittle, I would say offensive.
Well, perhaps. I'm not but I'm a descriptivist rather than a prescriptivist. I believe the language evolves over time. Anyway, okay. So they're
You hope forward.
well, no, I just mean evolves like as a physical system evolves. It changes over time.
Well, my answer to that is over my dead body.
Well, over time. Okay. Yeah, and there are a couple other nice properties of these things, and I just need to make sure that I attribute them to the right people. So I'm going to grab my notes for that, because that's the sort of mistake I don't want to make. I'm fine making mistakes with language, but with attributions, one should be careful. So I can never find the statement about. Well, okay. I feel like I'm just like missing an entire page of my notes. Let me just say that some other properties have been studied and other things are known about these things. And the particular question that we want to answer, this is very, very odd. The particular question we want to answer is one that, so let's say, other things are known in some cases. It's not even right. This is not even worth writing. So I think Casper's and FEMA showed that graph products preserve the Hagerup property under a couple mild assumptions. And then there are other things down this path. And we are interested in saying when they have free probability style regularity properties. And the one we care a lot about is this idea of strong one-boundedness, due to first Kenley Jung and then studied much more by Ben Hayes and by Damian Shevchenko and by a few others. Strong one-bounded. There we go. Okay, and so the idea of strong one-boundedness is that this is a property of a generating tuple a priori of a von Neumann algebra, which says that it is very difficult to approximate with matrices. It means that if you're looking for matrices that approximate the tuple in law, there are not very many. There are sort of as few as there can possibly be, or technically none is allowed. And so, yeah, let me say briefly what the actual definition is. There's this notion of the modified the modified free entropy dimension due to Voiculescu, and for a tuple of variables x1 through xn, this is defined to be equal to n minus the lim sup as epsilon tends to 0 of a certain free entropy style quantity where you have perturbed your generators by a little bit of free Brownian motion, divided by the log of the square root of epsilon. So this is your standard free entropy type thing. If you have not seen the definition before, giving you the formal definition will not be helpful, but it's just a count of how many matrices are there that approximate the law, the free probabilistic law of x plus root epsilon s. consider the family of all of them that approximated acceptably to some weak by being in some weak neighborhood of the law. And then you take the Lebesgue measure of that set, you take a logarithm of that, you normalize in order to make the limit actually work out correctly and to deal with the fact that you're using the Lebesgue measure specifically. You let a bunch of limits tend in the appropriate direction, and at the end, you wind up with a number.
Is that the formal definition?
No, that's a very informal definition.
Okay.
That's the spirit of where we're going. But I think if I were to write down the formal list of limits, it wouldn't actually help anyone who's not seen it before.
Oh, okay.
I have a simple question.
Mhm.
Would that number be more than X?
So the free entropy is bounded above by the variance of this quantity. It's bounded above by some function of the variance of these variables. So if your x's have finite L2 norm, there's a universal upper bound on this quantity, and epsilon is tending to 0. So this whole thing is at worst 0, or at best 0, depending on what you consider to be good or bad. It turns out that if x1 through xn are embeddable in R omega, then this quantity can be shown to not blow up worse than n over log root epsilon. Sorry, n times log root epsilon, which tells you that if these are R omega embeddable, this quantity is at least 0, and this piece is at most 0. Is at most 0, which means that the whole thing is at most n. So in fact, this quantity is in the set negative infinity union, the closed interval from 0 to n. And it has some nice properties. For example, if x1 through xn are freely independent, then the free entropy dimension of the tuple is the sum of their individual free entropy dimensions. If you have a single variable, then all you're doing is taking 1 minus the sum of the squares of the measures of the atoms in its spectral measure. So delta 0 of x is equal to 1 minus the sum over all real numbers t of the measure of the point t, spectral measure of x at the point t squared, additive over free things. And so, for example, the standard, if you take n freely independent semicircular random variables, or in fact, n freely independent variables with no atoms in their spectral measures, then the free entropy dimension will be n. And if you take, okay, and there are some other properties that are known about this, which are important. For example, if you have generators of a von Neumann algebra that has, which way does the implication go? If your von Neumann algebra has a Cartan subalgebra, then any generating set will have, and is R omega embeddable, any generating set will have free entropy dimension 1. Or if the free entropy dimension is more than 1, there's no Cartan. If the free entropy dimension is more than 1, then the von Neumann algebra these things generate is not prime, and does not have property gamma. These results are due mostly to Voiculescu, but there was one due to Gay that snuck in there as well. Okay, so it turns out, though, that this quantity here, I mentioned, so strong one-boundedness is a strengthening of the statement that the free entropy dimension is at most 1. So if the free entropy dimension is at most 1, it means that free entropy, as epsilon tends to 0, behaves no worse than n minus 1 times log epsilon plus something that tends to 0 relative to log root epsilon. And strong one-boundedness is a strengthening of that. So the tuple x1 through xn is strongly one-bounded. If the free entropy of the perturbed copies is less than or equal to n minus 1 log root epsilon plus a constant. right? So having free entropy at most one says that this should be some function of epsilon, which tends to 0 when divided by log root epsilon, as epsilon tends to 0. Strong one-boundedness says, in fact, it's a constant, or bounded above by a constant. And the remarkable thing, which Kenley Jung showed a few years ago, is that under very mild assumptions, like at least one of the xi's being diffuse, strong one-boundedness is a von Neumann property, in the sense that if one set of generators for the von Neumann algebra is strongly one-bounded, then all sets of generators are strongly one-bounded. And so this is quite nice because free entropy dimension often struggles at showing it's actually a property of the von Neumann. Well, and it's generally not known if it's a property of the von Neumann algebra. It's only known to depend on the generators, but some nice modifications, like strong one-boundedness, do actually just depend on the von Neumann algebra and not on the generators. So, for example, I think there's a paper of Michael Brennan from a few years ago where he shows that the free orthogonal quantum groups are strongly one-bounded, and therefore their von Neumann algebras are not free group factors, because the free group factors are known not to be strongly one-bounded, because they have a generating set with one-bounded entropy, not with microstates free entropy dimension strictly more than one, they can't be strongly one-bounded. So if you show something is strongly one-bounded, it's not a free group factor. Okay. So our goal is to understand when this property can appear in graph products, and to show that it really depends intimately on the structure of the graph we're actually using to define our independence relation. Let me pause briefly. Are there questions right now? Okay, great. And so, well, theorem due to the long list of co-authors. Suppose we have a graph G, and I want to have at least two vertices. So the statement is about something. Then we have the following two cases. If each, let's say, let MV be be tracial von Neumann algebras, and MG their graph product. Yep. Now I can state the conclusion. Then, first of all, if all of the MV are diffuse, then strong one-boundedness just comes down to connectedness of the graph and combinability. R diffuse and R omega embeddable. And I'll just abbreviate it this time to not get into an argument over the vowel. Then MG is strongly one-bounded. If and only if G is connected. And on the other hand, and I know that this is not an actual dichotomy of cases, if all the algebras are finite dimensional and not the scalars, and A inside of MG is the star algebra, not the von Neumann algebra. They generate then the vanishing of the first L2 Betti number of A implies that the graph product is strongly one-bounded. And we suspect, but cannot prove, that this is an if and only if. That this L2 Betti number construction is or obstruction is the only, or this L2 Betti number condition is the only thing you need to check. But we haven't shown that yet. We've only shown one implication. Let me remark on a couple of things. So the L2 Betti number of the algebra with respect to tau is asking for the dimension of the space of derivations from the algebra into algebra tensor algebra into the course bimodule, modded out by the inner derivations. So this condition is saying that the only derivations from A into its course bimodule are the inner ones. And then why should you expect that this being 0 tells you that M is strongly one-bounded? Well, this being 0 essentially means that there are a lot of relations between the generators of A. And that's how it can be difficult to define a derivation. That's what can force you to not have any interesting derivations. And on the other hand, lots of algebraic conditions on the generators of A tell you that if you take sort of matrices at random, they're unlikely to satisfy those algebraic conditions. In free entropy type arguments where you show, for example, that free entropy dimension greater than 1 implies you don't have property gamma, or property gamma implies that your free entropy dimension is at most 1, what you do is you say, if I have this asymptotically central sequence of unitaries, well, then I can sort of realize that algebraic constraint down on the level of matrix approximations. And then that means my matrix approximations are very constrained, and that's enough to force their volume to be small, and that's enough to force this quantity to be well behaved. So it's the same idea. If you have strong relations within your algebra, then that forces any matrix approximation to almost satisfy those same algebraic constraints. And so lots of algebraic constraints mean that you don't have many choice of microstates, and that's the intuition behind this kind of thing. Let me also as well say that there is a question of how computable this quantity is, and whether the first L2 Betti number of one of these algebras can actually effectively be computable. And even in the case where A is a group algebra and you have underlying groups, it can be challenging. There is a paper of Davis and Oken where Davis and Oken, where they write down an algorithm for computing the first L2 Betti number of a group algebra of a graph product of the group algebra of a graph product of groups. So finite groups and then a graph product of those. And they have a few more things in that paper which weren't directly of interest to us. The problem is that even their algorithm is somewhat challenging to actually run in practice.
What are the things that go into the computation? Do I need to know the group topology of all of them, or?
I don't remember. A year ago, we tried to see if we could actually resolve any interesting examples out of it, and we came to the conclusion that we couldn't. But I mean, again, you're assuming that there are finitely many finite groups, so you sort of know everything about them. I mean, the cases we're interested in are, well, you could even take finite abelian groups, and it would be interesting. Okay, so what are the ingredients that go into this theorem? What are the ingredients that go into this proof? There are two main bits that we care about. So one is, ooh, that felt weird. Right, there are two main bits that we care about. One is this, there's an argument due to Dimitrov that if you look at the group von Neumann algebra of a Sophic group with vanishing first L2 Betti number, then that von Neumann algebra is strongly one-bounded. And the argument more or less comes down to the fact, comes down to putting a few pieces together. And so for such a group, one of the things you can do is you can write down, oh, I probably need finitely generated, finitely presented in that list. Finitely generated, finitely presented, Sophic, vanishing first L2 Betti number implies strongly one-bounded. Okay, and how does the argument go? Well, if you write down, you can show sort of in general that if you have a bunch of polynomials which are satisfied by the generators of your von Neumann algebra, and you look at, so let's say F is a tuple of non-commuting, of polynomials and non-commuting indeterminates. Determinates, which are relations satisfied by the generators of your von Neumann algebra. Then if you look at the free difference quotient, the free Jacobian of F, adjoint times the free Jacobian of F, evaluated on X, and if this so happens to have, let me make sure I get the quantities. So I want the Fugger-Catazin determinant of this thing to be strictly positive. And I need one other condition, which is that the rank of df should be equal to n-1. Then a consequence is that w star of x is strongly one-bounded. Okay, and what Dima was able to show was that for Sophic groups with all these conditions, first of all, he can find a nice, if he plugs in the generators of the group von Neumann algebra into the free Jacobian of the relations on the group von Neumann algebra, then the rank turns out to depend on the first L2 Betti numbers. And when you have the assumption that it depends on the Betti numbers, the first and 0th Betti numbers. And when the first one vanishes and the 0th one vanishes, which happens as soon as your algebra is diffuse, then you have the appropriate rank that you're aiming for. And then second of all, he's able to show, because Sophic groups satisfy the determinant conjecture, it means that if you have a polynomial with integer coefficients and evaluate this determinant, you're going to get a positive number coming out. And more or less, the argument, the way this works is that you can show that your polynomial in group elements, because the group is Sophic, you can approximate it by permutation matrices, the same polynomial and permutation matrices, which have integer entries. And the determinant of a matrix with integer entries, well, the determinant of an invertible matrix with integer entries is at least 1. Or if you like, once you throw away the atom at 0, what you're left with, you can get a bound on this away from 0 just from the fact that your matrix has integer entries. And so that's where sophicity of the group comes in, and this is where vanishing L2 Betti number comes in. And what we're able to show is, well, we don't have, our algebras are not group von Neumann algebras anymore, so we don't have a nice generating set that we can approximate with permutation matrices. But we can show that there's a notion of algebraic sophicity which is good enough for us. And so what do we mean by this? Well, what does it mean for a group to be sophic? So a group gamma is sophic, means that for every epsilon greater than 0 and for every finite subset of gamma, there is a map phi going from gamma into some permutation group such that phi of 1 is 1, phi of g times phi of h times phi of gh inverse has very few fixed, has lots of fixed points, has 1 minus epsilon many fixed points with respect to the normalized counting measure. And last, that phi of g is almost free. So phi of g has epsilon many fixed points, and these are both for g and h in the finite set you're trying to approximate well. So any finite subset of the group you can approximate well with permutation matrices that have almost no fixed points, except the ones that are supposed to be identity, which have almost all fixed points. Okay. And if you think about what this condition about almost no fixed points or almost all fixed points means, what it means is that the diagonal of the permutation matrix, or the diagonal of any polynomial, low degree polynomial evaluated in the matrix, is almost constant. So our notion of algebraic sophicity is trying to catch sophicity in that we want representatives that have almost constant diagonals. And then the algebraic part is, well, we can't get integers anymore. We're going to weaken that condition and say we want to approximate things by matrices that have algebraic integer entries. So a tuple, a finite tuple, x1 through xn, in a tracial von Neumann algebra, we'll say is Galois bounded, or has a Galois bounded sequence of microstates, has a Galois bounded sequence of microstates. If there are matrices x1n through xn n, such that for any polynomial, for any non-commutative polynomial, the trace of the polynomial evaluated on the microstates minus the trace in the von Neumann algebra, the same polynomial evaluated on the generators, goes to 0. So they should be microstates. They should behave well for moments for any polynomial in the variables. The state should be approximately correct. But now I need to say something about what this Galois bounded bit means. I want each matrix to be an mn of, m capital N of O, where O is the ring of integers in some finite extension of Q. Some field K with index K over Q less than infinity. Okay, so I remind you briefly, what does it mean to be an algebraic integer? Well, what does it mean to be an algebraic number? To be an algebraic number means that you satisfy some polynomial with rational coefficients. To be an algebraic integer means you satisfy some polynomial with integer coefficients whose leading coefficient is 1. Okay, I also need two other technical assumptions here. I want that the supremum over all elements of the Galois group of K over Q of the norm of xi n, and the supremum also over n and I to be finite. So if your matrix has, for example, an entry that looks like 5 minus the square root of 2, then the action of the Galois group on that matrix might replace that 5 minus root 2 with 5 plus root 2. And I want, for any element of the Galois group, there to be a universal upper bound on the microstates. And last, I want the number of things in the orbit. The number of things. No, sorry, that should be handled by the Galois group being, by the field extension being finite. Oh no, okay, I think I've got all the conditions now. Good. So I want the entries to be algebraic integers. I want those integers to come from a finite extension of Q. And I want to make sure that when you act by the Galois group on one of the microstates, you can't blow up the norm. And it turns out that when you put all these things together and you do a little bit of work, you can show that this kind of determinant in a polynomial in these things, when you throw away the atom at 0, still needs to stay, well, yeah, still needs to stay away from 0. And the point is, well, with integers, you can't go less than 1. And on the other hand, if you have things in the algebraic ring of integers, you also need to stay away from 0 unless you're taking very large linear combinations, which will blow up under some element of the Galois group. So this condition of bound here forces us to not be using things that that have too large coefficients and linear combinations of the elements of the generators here. And then that forces us to be in some finite set that we can just push away from 0. So if you're in this setting, then you can get an equivalent of the determinant conjecture. But there's one other thing that we want in order to be algebraically sophic. I've got the algebraic bit, I still need the sophicity bit. And so what I want is that the tuple is algebraically sophic. If there are such microstates which additionally for any non-commutative polynomial P, it's asymptotically constant over the diagonal. And what I mean by that is that if I look at the projection onto the diagonal subalgebra of P of xn 1 through P of xn n, and I subtract the trace of that polynomial, P of n times the identity, that this tends to 0 as n tends to infinity, which is, if you think about it, just saying that all the things in my algebra are asymptotically constant on the diagonal, which is the same as saying that, which is inspired by the condition in sophic groups, that you can take permutation matrices which are asymptotically constant, which have no fixed points, except for the trivial element. Okay. The reason we want this condition is for the second bit of our argument, which, in the interest of time, I'm just going to say out loud and not say very much about, which is we want to, so we have now, oh yeah, one can also show that the n by n matrices are, the n by n matrices have an algebraically sophic set of generators. Any finite dimensional von Neumann algebra does, so does the von Neumann algebra of any Sophic group. Okay. What we want to show is that this is preserved by graph products. And so what we need to do is to say, if you have a bunch of algebras that individually have good algebraically Sophic approximations, then so does the graph product they generate. And here, so how do we take microstates for a bunch of individual algebras and get microstates for the graph product? Well, there's work I have with Benoit Collins from a couple of years ago during COVID, where we show that if you conjugate by Haar unitaries, but with certain tensor product structure and a large number of copies of tensor products of the n by n matrices, then based on exactly how you put the algebras into this larger tensor product, you embed each onto some subset of the tensor factors and conjugate by an according unitary, that this can give you graph independence for a graph that you choose. The problem is conjugating by Haar unitary matrices will destroy anything like having nice algebraic integer entries. So instead, we need to show that you can get something similar if you conjugate by permutation matrices, because that will preserve algebraic properties of the entries. But the cost of conjugating by random permutations instead of random unitaries is that you don't get graph independence in the limit. You only get graph independence with amalgamation over the diagonal. But if we assume that our microstates are already trivial over the diagonal, then graph independence with amalgamation over the diagonal is just graph independence. And so there's a long, intricate random matrix combinatorial argument to make all that go, which is a lot of fun. And if I had another hour, I would love to tell you all about it. But I see that we've run out of time, so I'll stop here. Thank you for your attention.